Today we are going to measure high voltage, though low amperage. We are going to use a battery-operated bug zapper, the one that you can buy in any store, and we disassemble it. I remove the capacitor, which is actually was not soldered well anyway. That's why I disassembled it. It was not working correctly. I also shorted the diode over there. So we are going to measure the output of the coil that's coming from on the output side. And how are we going to measure it? This is a 10 mega ohm resistor, and this is a 100 kilo ohm resistor rated for high voltage. So we are going to get a 100-to-1 ratio, reducing the voltage. So it will be okay for our Pico to measure that voltage. The output is about 1000 volts, and so I expect about 10 volts coming on the Pico. So let's take a look at the waveform. I also instructed the bug zapper to run automatically. Every 10 seconds I run it for half a second using a special circuit based on ESP8266 chip. Maybe I'm going to make a separate video about that, but we are going to have a half a second interval over here, and this is exactly what we see. And we see that it's a nice AC waveform. There is about 1 volt positive and minus 10 volts negative, and you see that minus 10 volts multiplied by 100 does make it minus 1000 volts being produced at the output of the circuit for the bug zapper. Now if you want to get a close-up, we are going to change the time base to, let's say, 100 microseconds per division and see what happens. So this is a pretty nice waveform, and you see that it has a very nice spike and actually a significant dwell time. We are going to turn off the device and measure this in the picoscope waveform to get the exact timing and voltages. So let's take a closer look. I put the cursors already. So we have the voltage going all the way to 1.1 volts on the Pico waveform, which means about 110 volts for the output of the device. And on the lowest side it's about minus 11 volts, meaning that it's around minus 1100 volts being produced. The distance between the peaks is approximately 220 microseconds, which corresponds to the frequency of about 4.5 kilohertz. So this is it for this experiment. We can measure high voltage by using a resistor divider and feed it into the picoscope up to 2000 volts, because the Pico can only accept plus minus 20 volts. And we can get a very nice waveform over here that basically tells us how this oscillator inside that circuit on this board, very small one, operates. One last experiment is checking the battery voltage while the device is turned on. So I'm just connecting the channel A to the battery, positive and negative, and then changing the settings to plus minus 1 volts AC, so that I want to capture the difference from the regular battery voltage. And we get quite a nice picture over here that we typically get a feedback from the circuit that can go all the way up to minus 0.02 volts, fairly high frequency of interference that lasts exactly for half a second that the device is turned on. So we can also check on a smaller time basis what exactly that interference is. Okay, it's hard to figure out what it is at 10 microseconds per division, so let's do it at 100 microseconds per division. Okay, now we can see it's sort of like a sawtooth wave going a little bit, yeah, pretty much 0.1 volt, and then a spike minus 0.1 to minus 0.2 volts. Well, that goes into our microprocessor, well, with some filtering, but apparently it doesn't even mind, so seems to be working fine for now. Well, this is quite a bit of interference going back.